Hi everyone. Since we got 5 likes on our previous video that I posted, which was on chapter 1, I decided to continue the series because that means that the video did help a few of you guys. And that's enough for me. In this video, as you saw in the title, we'll be going over chapter 2 of the Kaplan Biochemistry textbook, which is all about enzymes. Section 1 is talking about enzymes as biological catalysts. The book mentions these key features of enzymes, which are they lower activation energy, increase rate of reaction, they do not alter the equilibrium constant, are not changed or consumed in the reaction, are pH and temperature sensitive, they do not alter the overall free energy change, and lastly, they are specifically for a particular reaction or a class of reaction. We will talk about most of these features in this section. Before we move on to the enzyme classifications, just note that the active site is a location on the enzyme where the substrate is held during the chemical reaction, and substrate is the substance that the enzyme acts upon. Most enzymes have names ending in suffix "ase," and the name are usually descriptive. For example, lactase breaks down lactose. Very simple. And enzyme specificity is the property of enzyme and describes how restrictive the enzyme is in its choice of substrate. There are 6 categories of enzymes. So the first one on our list is oxidoreductases, which is a tongue twister, and they catalyze the transfer of electrons from one molecule to another, and because of that, they are used in oxidation reduction reactions. And the reductant would be the electron donor, and the oxidant would be the electron receiver. Oxidoreductases often do have cofactors that act as electron carriers, like nicotinamide adenine dinucleotide or nucleotide adenine dinucleotide phosphate. And enzymes that oxygen is their final electron acceptor include oxidase in their name. Next category is transferases. And as you can see in this example, they basically catalyze the transfer of a functional group from one molecule to another. Kinases fall under this category, but they only catalyze the transfer of a phosphate group, generally from ATP to another molecule. Next are the hydrolases, which catalyze the breaking of a compound into 2 molecules using water. They are mainly named only for their substrate. So, for example, here we have phosphatase, which cleaves a phosphate group from another molecule. Other hydrolases include peptidases, which break down proteins, nucleases, which break down nucleic acids, and lipases, which break down lipids. Lyases catalyze the cleave of one molecule into 2 products, as we can see here, and the reverse of it would be called synthase. So the reaction going this way would be catalyzed by lyases, and the reverse would be catalyzed by synthases. Next are the isomerases, and they sound like isomers, which, as we all know, are compounds that contain the exact same number of atoms but different arrangement of atoms. And that is what isomerases do. They catalyze the rearrangement of bonds within a molecule. So isomerase can also be classified as oxidoreductases, transferases, or lyases, depending on the mechanism of the enzyme. And the last category in our list are ligases. And they are like lyases, but they deal with bigger molecules and often need ATP. For example, ligases are very important in DNA replication, because they catalyze the connection of Okazaki fragments together in the lagging strand of the DNA. They also rejoin nicked DNA, which is very useful in DNA repair systems. So, how do enzymes make reactions billion times faster? So, enzymes lower the activation energy, which is the energy needed for a substrate to reach the transition state without changing the overall thermodynamics of the reaction. But they have a big impact on the kinetic of a reaction, which is because equilibrium can be achieved much faster, even though the equilibrium position does not change, as you can see here. Also, we do have two types of reaction, which are endergonic and exergonic. Endergonic reactions require energy input, which means they are non-spontaneous. And exergonic reactions are the opposite, so they do not need energy input, which makes them spontaneous. Okay, we are done with this section, which was section 1 of chapter 2, and I'm going to put the questions up for this section so you can test yourself. Section 2 is about mechanisms of enzyme activity. So, as I mentioned before, active site is the location in the enzyme where the substrate is held during a chemical reaction. And the substrate is the molecule that the enzyme acts upon. When the substrate and the enzyme are joined together physically, they are referred as enzyme substrate complex. So we have two theories that explain how enzymes and substrate interact with each other. First, we have a lock and key theory, which the name is very descriptive. So the enzyme would be in a special conformation, and only the substrate that fits it can bind to it, just like a key and a lock. The more scientifically accepted theory is the induced fit model. The book explains this one as a hand squeezing a stress ball, where the hand would be the substrate and the ball would be the enzyme. Because the induced fit model states the enzyme can change conformation and become a fit to the substrate, but that only happens with the desired and appropriate substrate. The book also splits the reaction into two parts. First, being the substrate is changing the conformation of the enzyme, or the hand squeezing the stress ball, which requires energy, and therefore the first part of the reaction is endergonic. And the opposite goes for the second part of the reaction, which is when we have the desired product, also known as letting go of the stress ball, which requires no energy. So this part of the reaction would be exergonic. Next, this section talks about cofactors and coenzymes. And some of the key features of them are these right here. They are non-protein small molecules which bind to active sites and carry charge and are kept at low concentration in the cell. But keep in mind that they are not the same. So here are the differences between them, but the most important one is that coenzymes are organic, like vitamins, but cofactors, on the other hand, are inorganic, like metal ions. The enzymes without cofactor are called apoenzymes, and the enzymes with cofactors are called holoenzymes. Cofactors are attached to enzymes in many different ways, ranging from weak non-covalent to strong covalent interactions. A coenzyme or a cofactor that is absolutely needed for an enzyme to function are called prosthetic groups. Are not limited to a single cofactor or coenzyme, so they can have multiple of them. Section 3 is about kinetics of the enzyme. So we'll be discussing the factors that can change the kinetics of the enzyme and the speed of our reaction. So let's say we have 100 enzymes and only 20 substrates. So that means we are nowhere near full speed. And like by speed, I mean the products made in a certain amount of time. So you can think about it like getting tasks done. And that reminds me of Among Us. But so the substrates as people working on tasks. So for example, let's say we have 100 tasks to do. So how many people do we need to get the job done the fastest way? And let's just say one task can be only done by one person, so no teamwork. Yes, so we would need 100 people to be the most productive, I guess. The maximum velocity is achieved when the number of enzymes and substrates are equal. And the maximum speed, and by speed I mean velocity, but so the maximum velocity is called the Vmax, which makes sense. Velocity, maximum velocity. As you can see, we have a graph here, and on the x-axis we have the substrate concentration, and on the y-axis we have the velocity of the reaction. And the blue line here indicates the Vmax, but it's important to know that the line does not show us the exact Vmax value, but it's very close to it. So how can we increase the rate of the reaction? If we want to increase the rate of the reaction, we have to add more enzyme, because as you can see here on the graph, the increase of substrate does not do anything after you basically hit the Vmax. But if we increase the enzyme, we would have a new higher Vmax. So using this formula, you can calculate the velocity of the reaction at any given point, which is velocity equals Vmax times substrate concentration over Km, which we will get into in a second, plus substrate concentration. So Km is the Michaelis-Menten constant, which is often used to compare enzyme, and basically Km is the substrate concentration when we are at half of the Vmax. So as you can see, we also have it on the graph here. And if you do a little bit of calculation with this formula, you will see that the Km equals to S when you're trying to find a Vmax over 2. And here are the calculations if you have trust issues like me. We use Km to compare enzymes. So what does a low Km mean? If we have a Km that is high, it means that the enzyme has the lower affinity for its substrate, because it requires a higher substrate concentration to be at half Vmax. So the second equation we have on this section is this, which is showing how kcat can be mathematically related to Vmax. Kcat is the turnover number of enzyme, which basically is the number of reaction processes that each active site catalyzes per unit of time, which would be like seconds. So let me expand this equation for you because it's kind of hard to fully understand it. So Vmax is a moles of product per second, which equals to the moles of enzyme times kcat, which is moles of product per second over moles of enzyme. And now when these two multiply, you can see how it will be Vmax. And by the way, most enzymes have kcat values from 101 to 103. So okay, now that we know what kcat is, we can just play around with it and replace the Vmax in our first equation with it. And it would be this equation right here. If we are at low concentrations and the Km is a lot larger than the substrate concentration, we can just remove the substrate concentration from the bottom, and we would end up with this equation. All right, Now we have a Lineweaver-Burk plot, which is a different type of graph that we saw earlier. But we're still dealing with the same equation, so nothing has changed. It's just a different graph. The importance of this graph is that the interception of the line with the y-axis will be 1 over Vmax. So unlike the first graph, this will give us the exact value of the Vmax and the Km. So yeah, and the line crossing the x-axis determines the Km value, but it's actually negative 1 over Km. So, you just multiply it and then you find Km.